Let x and y be jointly continuous random variables with the joint PDF given here. Find the marginal distribution of x and y. Are they independent? The second question is find the conditional PDF of x given y. And the third one, calculate the conditional expectation of x given y equals y and the conditional variance here. First, let's figure out the range of a value of x and y using a plot. Here we can see that x is between 0 and 1, so between 0 and 1. For each fixed x, y is between 0 and the square root of x. So for fixed x, y is between 0 and square root of x. So if you look at the possible value of x and y, lies in this region, right? So x is between 0 and 1. If you look at the overall value of y, it's also between 0 and 1. But for fixed x, y is from 0 to square root of x. Let's calculate the first one. Let's find the marginal densities of x and y. So marginal densities of x, for example, was equal to integral from negative infinity to positive infinity fxy x y dy. So when we calculate the marginal density of x, given the joint densities, we need to integrate out the y, right? That's the general formula to calculate marginal density of x, integrate out of the y. Now we know that the value of y is between 0 and the square root of x. So this is equal to from 0 to square root of x, and the density is 6 xy. So it's 6 xy dy. And this is equal to 3x squared. So let's write down the density of fx, because here x is between 0 and 1. So the density of fx, the density is equal to 3x squared, because x is between 0 and 1. So the overall value of x is between 0 and 1 here. So this is equal to 3x squared, and it's 0 other ways. So here's fx. Now let's look at the fy. Fy, again, this is equal to infinity, negative infinity, positive infinity, fxy, xy. Because we're looking at the density of y, so we need to integrate out the x. So this is equal to now let's look at the because we're trying to integrate out of the x. Let's look at the range of x given the y, right? So we know that the x is greater than square root of x is greater than y, so we can write this as x is greater than or equal to y squared, and we also know that y x is between 0 and 1, so this is must be less than or equal to 1. So here is the range of x given y, so between y squared and 1. So because here we are doing an integral with respect to x, and x is between y squared and 1, so this integral is from y squared to 1, and again 6xy dx. This is equal to 3y, 1 minus y to the fourth. So again, the possible value of y, the overall possible value of y, as we see in this plot, is between 0 and 1. So now let's write down the density function of y. So this is equal to 3y, 1 minus y to the fourth. When y is between 0 and 1, it's 0 other ways. So now we have the marginal density of y. Let's look at the b. B is to calculate the conditional density of x given y. So this is equal to, in general, to calculate the conditional density, we take the joint density divided by the marginal density here. So in general, to calculate the conditional density of x given y, this is equal to the joint density of x and y divided by the marginal density of y. We can just plug in because we know that fxy is equal to 6xy. So it's 6xy. And fy, we just calculate the marginal density here. It's 3y divided by 1 y to the fourth. So it's 3y. So this is 2x, because you can cancel this. 2x divided by 1 to the fourth. And note that we are looking at the density of x given y, and y is fixed now. So we know that x is, as we show here, x is between y squared and 1. So x must be between, for any given value of y, x must be between y squared and 1. Outside of this range, the density would be 0. So essentially, this is the conditional density is equal to this when x is less than or equal to 1 and greater than or equal to y squared. It would be 0 otherwise. So let's look at C. Find the conditional expectation and the conditional variance here, and C. So expected value of x given y equals y. This is equal to infinity, negative infinity, positive infinity, x, f, s given y, d of x. Again, this is a general formula. So to calculate the conditional expectation for x given y equals y, this is equal to the integral x times the conditional density of x given y, because we're computing the conditional expectation. So we need to replace this, we need to use the conditional density here. So this is equal to, because we're doing integral with respect to x, and we know that x is between y squared and 1. So this integral is from y squared to 1, and x, and the conditional density here, we just calculate this, it's equal to this. So it's 2x, 1 minus y to the fourth, dx, and this is equal to 2 times 1 minus y to the sixth, divided by 3 times 1 minus y to the fourth. Okay, now let's calculate the conditional expectations of x squared given y equals y. This is equal to negative infinity to positive infinity, x squared fxy, x given y, d of x. Again, to compute the expected value of x squared, or any function of x, this is equal to the integral from negative infinity to positive infinity, that a function of x multiplied the density dx. Now the function of x is x squared, so you just plug in the x squared here in the integral. So again, this is equal to, recall that the integral of x, because the density function as we show here, for fixed y, x is between y squared and 1, so the integral here is from y squared to 1, x squared times 2x divided by 1 y to the fourth, d of x, and this is equal to 1 minus y to the eighth divided by 2, 1 minus y to the 4. Now we're ready to calculate the conditional variance. So the conditional variance of x given y equals y is equal to expected value of x squared given y equals y, subtract expected value x given y equals y, and square. So now we already calculated the expected value of x squared given y equals y. We already calculated here. It's equal to this, so plug it in. 1 minus y to the eighth, 2, 1 minus y to the fourth. Subtract the expected value here. We calculate that one. It's here. Is equal to this number, so it's 2, 1 minus y to the sixth, divided by 3, 1 minus y to the 4, and take the square. This is it. Thank you for watching.